Welcome to our battery startup due diligence, a case study in Group 14. So again, those of you that have been to our previous talks, we do a Who's Doing It Right series, and we look at other startups and kind of grade them on a couple different things. We'll go over all that briefly, but this is a deeper dive on one company, so we can spend a little bit more time going over more specifics, and we're really excited to be doing this.
Yeah, and we really here try to, like, as it says here, enable conversations from different players. We try to give you a deep dive from the technical, so-called speak the unspoken of battery science, stuff that you aren't really going to hear, that's more tribal. And, you know, we'll try to share some things that are non-confidential that we know it might not be very much publicly available.
And then this is a technical due diligence and kind of a public information on sort of their marketing, planning, and finances due diligence. So we look at sort of the company, its value proposition, and its technology sort of market readiness. And again, from publicly available information, we both know a lot more, but we just can't talk about it. And we try not to talk about the people or the team. That's not really our role here, but just I have to say, looking at theirs, it was pretty good. So without further ado, Group 14. So on a core level, their basic product type is they are going to be a manufacturer for a silicon carbide blended material for lithium ion that really should be able to be a drop-in replacement for graphite anodes or silicon additives, which people are already using for graphite anodes. And their product should allow a boost in energy density and also improve cycling stability over current silicon products or current graphite products.
And as far as their technology is concerned, really, guys, it's just silicon deposited inside of an activated carbon matrix. Okay. So this is a little bit of how we do our ratings. We've simplified it up. Basically, if it's purple or a 5, it's perfect. 4 is great. 3 is above average. 2 average. 1 poor. And then, you know, if you're bad, it's dead, Jim. Look, it's done. It's no good. And there's only one company, and that's Oxus. Oxus falls into the it's dead Jim category right now.
They're surviving the valley of death because they died. Yeah. And so we will be releasing these slides. So these are all going to be available. Here's a little bit more of a breakdown on our grading system. If you want some more detail, we're not going to go into that for this, though, just because it's pretty self-explanatory when you read it. So first section. So the first thing we talk about is surviving the valley of death. And basically, this is the company's finances, financial preparations, investors, partnerships, and how they're going to basically spend their money going down into the valley and hopefully start making product, start making a profit, have that outpace their expenses, and then head back up, right? And so really, most of the companies we're talking about are somewhere from here to here, and they're basically, as they get more and more money and spend more and more, they're rocketing down into the valley, and hopefully their momentum is enough to bring them up the other side and kind of get them past here to where they finally have broken even with their investments and are able to then start being a profitable company, as opposed to a losing money and growing in market share, for example, which a lot of other things are still doing right now.
Yeah, and you'll notice the kind of the waves here, guys, right? Every company goes through 2 debt valleys, essentially, right? There's one, you've made something, people have bought it, it's becoming successful, it makes its way into an application, and then you got to build factories, and those are inherently not cheap, and then you go back into debt, and then you got to figure out how to make it most efficiently, right? It's almost like the far left valley is parts per mil or ppm for parts per million. You're really focused on science, and the right side is how many parts are you making per minute? So you move into that cross point.
And we've added a couple of new sections to the traditional valley of death thing here, just because we've started talking about them, and we'll get more into that, into the pain points for Group 14. But you know, you can have your first business success and still be in deep trouble going forward, especially if other technologies replace you or you can't protect your IP. So more about that later. So without further ado, the actual information we're going to be going over for this and kind of why we think it matters. So there's a bunch of buckets of things we look at. The founded and headquarters piece aren't that important. We just have them there for the information. But the things that Jeff and I really look at when we look at companies are their current and pending patents, their number of employees, and who they're hiring, because who they're hiring really tells you on what they're doing now, what they're having trouble with, and what they think they're going to need in the future. So in addition to that, you look at their funding rounds, the total funding, the key investors in both the funding rounds and any joint ventures, which is very relevant for Group 14, revenue streams, and then any manufacturing plants and kind of core value proposition and business plan. So we'll kind of run through those one at a time. I figure I'm going to start with job postings from the right side and go to the left. But Not a lot of job postings on LinkedIn, 69 employees on LinkedIn, 100 total, and that's a reported number that they gave us. And actually, at this point, I would actually just like to thank Group14, and they actually gave us a quick interview on Thursday to go over our presentation, correct us where we had a couple of things wrong, and give us a bunch more public information that we were able to use to make it a lot better. So just want to give them a shout out for that and really appreciate it. So that 100 number is directly from them as how many people they have right now, since not everyone uses LinkedIn. But they really only have, those 5 job postings that we could find, and they're all for basically plant scaling control management. And so it's not necessarily enough to build a new plant, which we thought was a little odd. Maybe they're still kind of putting that into place. From you'll see from the amount of money they got is they just got a very large 400 million round, you can see on the left. So we would have expected more job postings, so this might be coming in the future. But they are definitely hiring people for production and plant management and scaling. And that's what they say they're doing, and that's what they need to do. So that was very positive to us. Their core value proposition, again, is they're making a material that should be, higher energy, better stability for anodes. And their other kind of values are they're American made, so they're going to get in all of the, IRA money that was just announced. They're a neighbor of EVs and eVTOLs. They have potentially lighter weight packs, and they're also doing some interesting modular fab scaling. And their business plan is to really develop and manufacture the material, but also develop these sort of modular sets for manufacturing the material. And you'll see that a little bit when we talk about their GVs that they're doing with people. So they have 3 plants right now. One is a demo plant, which is their BAM1 production line in Washington, and it's been online since April of last year, about 120 tons a year of production, and they're shipping at some amount of that capacity to customers already. So they actually already have a revenue stream. It's not public because they're a private company and they wouldn't give me the info. I tried. The 2 more interesting ones, though, is they have a JV with SK Materials, and that's being installed in South Korea, and that's a 2,000 ton per year plant that's supposed to come online in about January of next year in 2023. So pretty soon. That's pretty exciting. That's an enormous amount of material. And then they have another one announced, their BAM2 facility in I think it's supposed to be in Washington. They're still it's still basically an announcement phase, but that's going to be kind of partnering with REC, which we'll talk more about later. And that's going to start at 2,000 tons a year and scale to maybe 12, which is, again, a huge amount of production. So current income coming from their BAM1 facility and potential income coming from their JV in Korea and their BAM2 facility. In terms of their funding, they've gotten pretty traditional kind of, series early all the way to C now at this point, where a little bit of money to scale, a little bit of a venture round, a couple of good grant proposals, which is actually where we got a lot of our information, were the 3 grant proposals they've gotten and their annual merit reviews. It's a great place. It's a great way to find out information about a company. Is you can go look up what they're reporting to the DOE or USABC or RPE for the money that they've been given, and you'll usually get a lot more detail, cycle rates and performance, cell size, which you will never see in a publication that's like a public announcement. And then the big one is they just got 400 million, mostly from Porsche, but a series of other investors, and that's really the critical piece here. Is they just got that in May. And that's what they're going to be using to kind of co-invest with these other companies on the JV facility in Korea and building out the one in Washington with REC.
Yeah, and I would definitely, guys, just keep in the back of your head, they had a sum gross total of $60 million in funding up until April of 2022. And then suddenly they got almost 6 times that money in one round. And another thing to keep in the back of your head, guys, is they're building a plant with SK Materials in Korea. You do not build a plant unless there's some amount of confidence in the thing that you're putting in it.
And we'll cover that in a little bit more detail on a later slide. But those are some of the things we thought were very interesting, is that they're already basically partnered with big customers that will explain why those people are important, and then sort of how that architecture works in the battery industry value chain. So next slide. This one's just a really quick thing, sort of how they play into the battery ecosystem, so specifically the silicon ecosystem. So we've looked at all these other companies previously in our Who's Doing It Right, Silicons Part 1 and 2, which there's videos on our YouTube for. But just very quickly, right, SilaNano, who's a material maker, There's Enevate, who basically develops technology and then wants to license it to people doing silicon anode production. There's Enovix, which has their own special silicon anode type and equipment and process, and then they're trying to use it to make cells. And then the same thing with Amprius. They have their own special equipment, process, and anode type, which they're using to make cells. So Group14 is another material maker. And if you really classify them by competitors, Enovate's not really a competitor. They're basically a big arsenal of patents that somebody can either use to try to get into silicon or block somebody else with silicon. So that's kind of its own thing. Sila's the material maker that really would be competing with Group14. And then companies like Enovix and Amprius are really, they're competing with the cell makers, not really with Group14, because they don't have the same customer base. And also StoreDot, who's not on here, is in the same boat. And actually, it looks like they're going to be buying material from Group14. So that's the opposite of a competitor, right?
And what I would add here too, there's another, like a little bit of a bucket, even between Enovix, Amprius, and Sila, right? Amprius is making their own material and then making their own cells and designing their own cells. Enovix is just designing their own cells. Their material is probably bought. Sila is just, they make cells, but really they're selling you material or anode coatings, right? So they're actually completely different stages of the value chain in terms of what their end goal is. So if you try to talk to any of these people, which we have, most of the time they'll tell you that they're not a competitor with each other. But I also find that hard to believe.
Yeah. This is specifically, the answer I was given that I believe I'm allowed to give out is that they actually view Sila as kind of a sort of a not so much a competitor, but kind of almost a partner pioneering people buying silicon materials. And that ultimately the space is they think it's going to be so big that neither one would be able to supply the market. So it will be slightly different performance, different variation materials that are available for people to buy. They already kind of have their own partners for manufacturing, probably their own cell makers lined up and their own car makers to buy the cells at the end, because they have very different funders at this point. So anyway, we just thought that was interesting. And we mapped out here just kind of some of the things we look at. So it's total employees, sort of investment to date, last round evaluations, if they're public or not, and what those are valued at. The other interesting thing here is all the other ones are much, much earlier than Group14. It's a much later company. Before we'd even done any of our stuff, I already knew about all the other ones on the list, and even StoreDot. I really hadn't known much about Group14 until people started asking for it after we'd done our Who's Doing It Right in Silicon series. And so it's been very interesting for me to learn about them. And a lot of their stuff is obviously very recent because they're only a couple of years old, whereas all the other ones go back at least 4, if not, 10 years, right? Mm-hmm. So next slide. So, and these are the other kind of two big pieces. So in terms of direct investment, Porsche was the one that put in most of the money in a lot of VCs, but SK Materials has jointly invested $726 million. And there's a link here. It's publicly available on different news articles, but $726 million with them to build a plant in Korea. And so SK has a 75% stake in that, and the Group14 has a 25%, and that's the 2 tons of material production, hopefully online in January of this year. That's what they said. And maybe that's when the plant turns on, and then they start scaling, and we'll see. But that's a really big deal, and people don't put that kind of money into a plant, and they don't turn that plant on until someone's actually going to buy the materials to put into batteries. So what that probably means is that they have lined up companies in Korea, which there's 3, LG, SK, and Samsung, right? So there's 3, probably SK just because it's part of the SK group, but any of them. And they've already basically agreed to buy the material and put them into cells, because there's no way you would build this much of a plant and then spend that much on materials to make something that you're not going to be able to sell. So that's actually pretty exciting. So we would maybe expect to see these added in, maybe at first low concentrations into existing cell lines where people are already putting in kind of 3 to 9% silicon additives into their graphite. And maybe even, higher percentages, 20, 25, maybe even majority, which is something that Group14 claims their material can do.
Yeah, and what I would say, guys, kind of as a teaser, because I see the chat going off, let us get to like the whole slide, but basically, right, silicon companies all do things, and when we get to the pain points, we'll explain what their greatest success is, but also what it is going to be their greatest weakness.
Yeah, and thank you, Rob, for that. Yeah, we didn't choose to talk much about the Energy 2 stuff, which sold to BASF, and they spun Group14's technology out of that kind of interaction. it speaks to kind of the team's experience and background, and we just try not to focus on that piece specifically because we don't like talking about individuals. But that is a good point, and that is a big advantage in that basically it came out of another technology development group that focuses on similar materials, that understands the architecture, and that was working with somebody like, and that was acquired by somebody like BASF, which really knows how to do this stuff, right? So that's a really nice kind of check mark that we thought about. We just didn't include a lot of that in the presentation. So then the other one is, we'll talk more about SK Materials and REC Silicon later, but then their other big one that they're doing is their BAM2 facility in Washington, which will start at the same 2,000 tons, which is sort of their modular size for like sort of a single module in their sort of factory plans. And they're eventually planning to scale that 1 to 6. And so 6, will be 12,000 tons totally when they finally get there. There's no information that I could find on the total investment or the ownership of the BAM2 facility in Washington, but basically it's 2 to 6 times. It's more than 1 times, maybe as many as 6 times bigger. So proportionally, probably the investment going into it is much bigger. So I'm actually excited to kind of see what that is eventually when they announce it. But like it won't be 4.3 billion because there's economies of scale, and you buy the factory once and then you put in the modules. You don't put in 6 factories worth of costs, but it's going to be more than 726 million and less than that number in billions. And so I'm really excited to actually see what that is when they do that. Okay, so next slide. So, Jeff, you want to cover this?
Yeah, so kind of this is our engineering into the box section. What we wanted to do is kind of give you a breakdown of really what the ecosystem kind of looks at from 1 to 20,000 foot level, and then we'll get a little bit deeper into it. But basically, you can break most of batteries into 4 things, right? You have raw materials and their extraction and processing. You got people like Nano One, you got Cobalt, SK Materials would fall into that, right? REC Silicon would fall into that, even Dow, BASF. We have L component people, right? That's where you see a lot of the people we talk about today are people in other competitors, right? Scion, Cuberg, Sila, Prologium, 24M, SES, Oxys, now dead. But they would fall into that cell components area. You have battery management people, right? You have Voltaic is a great example of people who not only want to get you into the analytics side, but also help with the battery management and help you understand your batteries better to manage them better. And then also you have the sustainability, right? Ascend, Redwood Materials, people who are saying at some point we run out of metal, we need to fix it and we need to recycle it somehow. And I know that there's a lot of conversation to be had there, but for the interest of this conversation, right, Group 14 is actually in the left 2 components. But if you go to the next slide, you'll really see the breakdown. So basically you have raw material mining and production. Those generally tend to flow into some sort of refinement, right? So Group 14 makes a material. They are not at the place mining that material, getting the raw. They are just merely a refiner of it. Those refined materials, whether that be copper, aluminum, nickel, NMC, or just the graphite, those all go into your foils, anode, cathode separators. They get processed over to somebody who would be in that range. And in that range, you have a lot of what we'd call the assemblers, like an Enovix would fall into this range. Who else? Like Amprius would be the first 2 raw materials and the foils, right? And then you also have people like Ferrosis, right? And then at the kind of the right, you go towards the end usage application, and then you have the recyclers on the bottom who try to upcycle or recycle. And then at the top, you kind of got the Arbins and the biologics and the Digitrons and the like Mans AGs, people who are making you the equipment. They have no business wanting to make materials, no business wanting to make you a battery. They just want to sell you manufacturing equipment or testing equipment. Okay. So if we do this for Group 14, this is what it looks like, guys. So raw materials, that's usually coming from Dow. That's usually coming from any of those people up there in terms of where you're getting your material. Now for raw materials for them, they're getting polymers and they're getting silane, some version of silane gas. That is the 2 components that they're getting. They are then refining that. And in there, they have SK Materials and REC Silicon, which are the new joint ventures. So Group 14.
Who, by the way, are also the sort of #1 makers of the silicon and the silane that are being used in the process.
Exactly.
So it's a wonderful partnership where basically they're kind of being vertically integrated and then either JV'd or partnershiped or licensing, whatever the model is for the other factory that we don't know yet. being basically integrated into those companies as a value proposition to then sell it towards the people actually making the components and making the cells.
And the handshaking doesn't end with SK and REC Silicon. They actually have partnerships with Arkema, Ferrosis, to actually help them build their batteries for them. So Group14 is making the materials, but they aren't the ones building their materials themselves. They're actually leveraging Ferrosis, Arkema, SK Materials, Silatronics for their electrolyte development, right? So they have a lot of different things. Then they go into cell production, and this is actually where we mentioned earlier, they're even partnered with StoreDot. So a lot of the cells StoreDot makes for their fast charging silicon, high energy stuff, actually that silicon material is coming from Group14. And then as far as pack goes, we have StoreDot in there because they have the whole BMS that they're trying to sell for fast charging. And then Porsche is going to be making their pack. And there's a lot of experience right there because Porsche has the Taycan, Porsche has several EVs that they can leverage that on, or several hybrid systems where they know how to manage the batteries. The interesting thing here, and Aubert and I actually had a lot of discussion on this, is if you look at all the players in the buckets, you kind of have to lump Group14 into manufacturing equipment to be competitive. And we'll get a little bit into that later, but they need to be in that bucket or this whole thing breaks down a little bit for them in the long run.
Okay. So just real quickly for people that aren't familiar, so REC Silicon is the world's largest producer of silane gas. They also do a lot of other silicon materials for wafers and in semiconductor and in high purity for solar, along with other things, of course, but those are the relevant ones. And then same thing with SK. They're the second largest producer of silane, and the same thing with silicon. And so really the core materials going into Group14 stuff is either the extra raw powders or scrap from their other silicon industries, and then the silane gases, which they're the prime producers of. So it's both a sort of vertical integration play and also a helping fund and get a company going that's going to be buying your materials as either the JV or the factory or the cell phone factory. All of the material, all the factories they're making, so that the BAM1 basically facility in Washington was kind of like a sub-module test, and it's 120 tons a year. And basically their sort of full module is a 2,000 ton a year. And that's basically whatever that is 17 of those or something to get to that range. And you basically just take those and you stack them up in a bigger module. You plan for that whole module from a facilities perspective, environmental perspective. Silane gas management is not an easy thing to do perspective. And then you can take those and scale them into multiple units in a larger factory. And that's exactly what they're doing. So the JV with SK Materials in South Korea is one of those big modules, 2,000 tons a year. And the BAM2 facility is going to start as 1 and hopefully scale to 6.
A lot of this too, right? If you look at it from engineering into the box, they've done it really correctly, right? Instead of trying to onboard all the hurdles and troubles that you would see most battery startups do, where they say, I'm going to do everything. They've said, I'm going to do this very little thing, and then I'm going to shake hands with everyone around me and let them in the building and see what I am doing, and I'm going to have them help me. We've seen this strategy with the Soteria is another good example of somebody who did this strategy that's been very successful, right? They went to the Lay's factory and said, hey, you guys are experts in putting metal on bags for potato chips. Can you help us develop this film? So they're following the same strategy. And as far as going into the box, they've kept it really small and they're doing it really correctly. They're not trying to sell you an anode. They're trying to sell you a material, which for all they care could be 2% of your anode to 50% or all of your anode, right?
Yeah. So next section is pain points. And so typically we talk about this as overcoming the hurdles as you go from kind of small lab scale to bench scale to pilot to manufacturing. We added a few other things that are sort of not as technical, but that really matter from a company value proposition, long-term sustainability perspective as you scale those as well, which we'll talk about shortly. And that's why we highlighted some of those things earlier, which will make sense once we talk about them. So first, Jeff's going to kind of go over their process on how they make their material.
So if you're familiar with Sila Technologies, this will look actually really similar to you. So the core crux of their system is they have a polymer, which they put in a crucible or some sort of fixed powder bed, or maybe they have some agitation, I don't know. And they then carbonize it to get really high, get basically rid of everything but carbon. And when they do that, you're left with just a activated carbon for the most part, right? So first, step one, they're doing it well because they're doing it in Washington. They're at 11 cents a kilowatt hour versus 18, and most highly energetic processes or thermal reactors are going to be energy hogs because you lose a lot of your energy to dissipating the heat elsewhere within the system. And then two, what they do afterwards, they have that activated carbon, is they take silane gas and they inject it, and then they crack the silane gas. So they're basically ionizing it. And that is going into the pores of the activated carbon and depositing a certain level of silicon. Now, one thing you have to understand here, guys, is actually this technology from Energy 2 and everything, right? It was born out of gas absorption activated carbon. So they were looking at activated carbons, which would absorb gas, which kind of flows into this whole, we are going to make silane and deposit silane gas into this. Now, when you talk about the pain points of this whole system, really it's coming down to particle manufacturing and how evenly you can control deposition, right? So on the left bottom here, they have this particle design where they show you this almost wafer looking thing with 50% void, 50% silicon. I can tell you right now, on an activated carbon, unless you have the world's narrowest pore size distribution and the best flow of getting access to all the pores, aka all those pores exist on the surface and nowhere else, it is very hard to deposit an even amount of silicon within the material. Now, from a pain points point of view, they're going to have a lot of scale up issues, right? And this is where you're starting to see SK Materials and REC Silicon come into play. They've made materials, they've scaled it up, they're building factories together, they're building reactors together, and they're going in. Now, as Aubert alluded to earlier, we generally look at just the technology, but we decided that, it was really hard to say anything bad about the technology, right? We've known Sila's been doing it. Sila has been very successful. They've made it into a consumer application. So we wanted to understand, how do they differentiate from Sila, and how is this going to be their pain point, right? So both are building factories in Washington. We know it has low energy. That's great for these thermal reactions or CVD reactions that these silicon makers use. They both have a activated carbon, right? Which is all to say is they have something that's porous that they can shove silicon in, and they do it by cracking the silane. So they both use silane, and both of them want to be in EVs. So the real question is, how do you protect yourself, right? How in 3 to 5 years can you protect yourself? And this is where IP is important, but also what you do is important, right? If you look at cracking silane gas, there's only so many gases. Like there's siloxane, there's silane, there's monosilane, and there's only so many ways for you to apply energy to force ionization of silicon and then deposit it. Similarly, there are only so many ways to make activated carbon. And the problem with the IP space, right, too, is there's a broad window of people who have claimed carbons and have material claims already that are far wide reaching, and they cover things from everything from a 0.5 nanometer pore to 100 nanometer pore in the same exact breadth of width. So what we really want to do is are they have well planned for enforceable patents, right? Like between them and Sila, how much are they cannibalizing each other, right?
The core question there really is, let's say a third party started manufacturing the same or similar materials in China or somewhere else. Would you be able to buy a battery with both of the different companies' materials, cycle them, autopsy them, take the materials out, and do testing that could definitively prove that one was from them and one was from somebody else that wasn't them, and be able to, for example, win an ITC case? And if you can't, that's a real problem in 3 to 5 years. When you've developed everything, they can hire your engineers and repeat it somewhere else, maybe for cheaper. And so that's one of my big questions that I didn't see a really good answer to. A lot of companies have this problem, and we haven't beaten up other companies we've reviewed for this before, but really because of the way this is working, you're sharing your technology with your partners that are helping you build the factories, so the information is going to be widely distributed, and it becomes a really big issue, especially when it's, there's factories in Korea, there might be factories in China, there's going to be factories in the US. It's really easy to lose control of your value proposition if you can't really control your equipment and your process. And so that's what we identified as one of their big pain points. So kind of the questions we'd like to know is how they're going to control the process when they're working with SK materials and REC silicon so that they remain in control of it. I mean, trade secrets work only to some extent, right? So unless they have really well enforced patents or like ironclad relationship agreements, which again only last a certain number of years, kind of what happens during that time and after that time. And then also, you know, will they be able to kind of innovate faster internally than their partners can or competitors can with the same stuff, and therefore stay ahead and therefore kind of always be able to get the next order and then the next factory?
Yeah, and a good example of this, guys, is kind of in the reverse, right? Which is if you look at like Tesla and Panasonic, right? They shared the walls of the same building together. They shared all of the information. They were able to look at each other's things, and although Panasonic probably kept most of their trade secrets really well hidden, Tesla was able to learn, advance, and innovate. And at some point, SK Materials and REC Silicon and SK Innovation have to make a build buy decision in the future after this JV. And the question will be, can they protect their technology well enough to make SK and all of them say, we're going to buy? Okay. And we haven't seen a good answer to that so far.
And again, we probably wouldn't, because that's going to be very proprietary and controlled. But it's a big question that we had. So we are running a little bit low on time, so we're going to try to speed up a little bit. So the next is basically matching the market. And as many of you know, people kind of try to force their battery chemistries into markets they don't belong to, specifically EVs in many cases. And so really you have to match the chemistry and performance of your battery to a market, not the other way around. So what we're looking at here is there's not a lot of really good information on the cells. And the reason for that is because Group14 doesn't make them. So you have to find stuff from StoreDot or Ferrosys or their reports from their DOE projects. And so, you know, you see here, you know, this is from one of the DOE projects. It's a 0.4 amp hour cell, which is not a great demonstration of performance in a scaled cell, but it's at least, you know, decent cycle rate, decent cycle life, you know, real cells, you know, and you get a pretty decent performance. These are what they're reporting in those government grant merit reviews on what they got. So that's kind of the closest you get to sort of valid cell cycling to what we were able to really find for them. And then there's another thing where we're basically, you know, same thing, you get the announcements from StoreDot and the announcements from Ferrosys on what they were able to achieve with Group14's material. So it's not exactly what we want to see from a large reproducible data set of somebody's material, but it's customer data, it's third party, it's, you know, maybe slightly exaggerated claims from the customers because they want to sell stuff, but it looks good. And even, you know, even has sort of charge rates for the cycles, which a lot of people don't share, which we like to see. So I did a little bit of very ugly napkin math, and I absolutely understand that 0 to 80% is not a normal charge discharge, and you change the rates during it. But just what that basically means is that if it was from 0 to 100%, you're getting about 4.8 C rate average for the whole charge, and that's actually pretty good to get that many cycles with that energy density, right? As you increase charge rate, you just completely destroy. You either have to completely redesign the cell to be a higher rate cell versus higher energy density, or you just destroy the cell. So you're always going to lose energy density when you do that. And the Ferrosys cells, again, you know, C/3 is a respectable rate. A lot of times that's what kind of the USABC DOE automotive stuff want to see as kind of like a base usage for the cells. And I guess the question is, I couldn't find information to post here, Tom, but one of the ones Ferrosys was building was an 82 amp hour cell. And I don't think those are publicly available yet, other than that they are. And I'm really excited to see how it scales in a real form factor. Because like your question basically alludes to, that's a really big deal. Really tiny batteries are in some cases a lot easier than really big ones.
You can get away with everything work. You can get away with murder in a small, less than an amp hour cell.
Yeah.
But if I had been thinking, the reason they might be doing such small test cells.
Could I ask you to not talk until we finish and then ask questions then? And then I would love to hear whatever you're going to say.
So not going to spend a ton of time here, guys, because we are time constrained and we're trying to make it to the end, or at least most of the way through. But basically, this is how the market looks right now. Now, we don't have everyone here. I understand that, but this is where you see it. You can kind of see StoreDot, Group14. They're all going to be in this little area, and where you can see Sila. Sila's numbers are actually baked on the Whoop Watch battery. So what I would say is, some LG, as long as they're close to that, they're probably telling you the truth. Anything above the solid energy line, probably a little bit of fluffing. A little bit of fluffiness going on. But next slide. As far as the matching the market goes, guys, if you look at lithium ion or silicon ion batteries, as we're dubbing it as shorthand, we know that's not probably the best naming convention. It's squarely within their goal, right? Automotive is probably going to be best. It's watt hours per liter base. That's where silicon strives or lithium metal strives. But also you're going to see them in the consumer electronics market. And we see a lot of that really from Sila Technologies, right? The wood watch, they're going to low C rate, high margin goods, right? And they're also aiming to be with automotive. So let's going into Mercedes, Group14 is doing Porsche. So this is all in alignment with the technology. So we were actually pretty favorable with how they were positioning themselves. They said nothing of aerospace, and we thought that was a pretty good foot forward.
Yeah, and I just want to say really quickly, but basically both of these are Jeff's two babies that he's put together. He's put an enormous amount of effort into making a list with all the commercial cell data, and then also everyone's claimed data from either their marketing materials, their public announcements, or even their like DOE reports. So it's this one we had to place the logos by hand, so there might be some problems with the overlap, but like we have the data for all of these from basically either spec sheets or the claimed and market ones. And we've been matching those kind of to the different technologies. And so these will both improve as we have more free time. So look forward to updates on these, but they were pretty exciting to me that we actually have kind of real data for those now to look at. So do we like them? So basically we're going to give kind of a good, bad, or neutral, or sort of doesn't apply grade to a couple different buckets. And we'll go over those here. So valid cell cycling conditions, we gave them a pass because it is third-party customer data. And even though those customers are incentivized to give really good results to sell cells, it's still third-party data from customers who are using your material. Not overhyped, I don't think so. I think they're pretty reasonable about what they're trying to do and what the goal is and how to do it. So we gave them a positive for that. Reproducible data sets is hard because we just haven't seen them. And like your point exactly earlier, Tom, 0.4 amp hour cells is not reproducible data sets of valid cell size, right? So uses total cell weight for energy density. We think so from the things we've seen in the DOE presentations from Ferrasys on Group14. So I think, and then not quietly changing procedure or layout of materials. That's really a thing that cell makers do. And so we're giving them a wave on that. They're definitely changing stuff between different sets of data, but that's customer data. So we didn't grade them badly for that, but that is a black mark. And then don't quote cost only in raw materials. That's hard to do because we don't have their cost data. And then don't compare yourself against old battery data. Nope, they're comparing against new. The numbers in their stuff is current sort of state-of-the-art market. And substance and marketing over PowerPoint specs, I think so.
Yeah, and if we go to the next slide, you can kind of see we gave them a 4+ out of 5. The reality is the biggest issue, and we kind of alluded this, we'll talk about it for the last 20 seconds, is their pain points. That's really what's dragging them down, right? They're sharing walls with SK Materials, somebody who knows how to make batteries better than them. So unless they control the actual equipment, kind of like an applied, at some point we have to be concerned about them getting leapfrogged by the people they're shaking hands with. You want to say anything else, Jeff? No, I mean, I think let's get to the questions. I know Luke wanted to talk about the limitations, I think it was in the chat.
I was just saying, no matter how nice it would be electrically for a phone battery or a laptop battery or whatever, if the silicon anode content goes over a threshold where the thermal runaway behavior is, let's say,
more Bernie,
permanently disfiguring or life-threatening, like we all carry a phone in our pocket. Sometimes you fall on something pokey, or sometimes you walk into a sharp edge of a table, and today your phone goes into it's usually LCO, and it's kind of a kitten, you get some electrolyte vapor and maybe a gentle fire. But in high silicon anode content test, you get hundreds of kilowatts, even from small cells, hundreds of kilowatts of thermal radiated power, and you leave molten metal behind, and it even cuts into stainless and other things around it. And so you wouldn't feasibly be able to package it in a phone in a way that wouldn't maim, disfigure, or kill the user in the event they tripped and fell on something pokey or whatever. Yeah. Just something to consider.
I agree. And, kind of to Jeff and I, really silicon is for higher energy density meeting applications, not so much for the consumer electronics, but maybe more like, the drones, aerospace, CV, and maybe EV. I disagree a little bit with that, but.
So the interesting, I think, with Group 14 is that's not their problem, right? Like silicon as an application in a market isn't Group 14's problem. Group 14's problem is protecting themselves from being essentially out innovated in 3 to 4 years by companies with a lot more money. Because they're shaking hands.
They have a little bit of a problem. If I agree with Aubert exactly, actually, when he said the real market for silicon anode material, and you hit it on the head, Aubert. But does the business still work well if that is the real market?
That's a great question. That's a really good question. And the answer is everyone goes towards EVs because of just market share and the ability to sell, so much of your product that you could never produce it. Mm-hmm. When you go towards other smaller markets where performance matters, you can command a premium. No one wants to pay the premium, but if you're the only one that enables it, you can get it. But that's not what people put, billions of dollars in for a factory to make, to have a, $30 million business.
So Group 14 is they're making a factory to make thousands of tons. You don't build that factory unless your confidence level for the applications that it's going to go into is high. Yeah. Right. You don't even break ground.
From a factory perspective, people do whatever they get funded to do, and construction workers will dig wherever you tell them.
Yeah.
But I'm just saying, I know it makes phenomenal electrical performance, but if the realistic market is what Aubert said, and I totally agree with him, that is the realistic market. How many thousands of tons does that entire market consume? Because I think we both know if you added up all the drone batteries in the world, it's what is it, like 10 megawatt hours or something? It's insignificant, right?
I've got a couple things I could say on that. So one of them is just, their little pilot plant, the 120 tons a year. We did some back of the envelope calculations, and that's it really depends on the percentages you mix it in at, but you can get something like sort of 0.7 gigawatt hours of battery production out of those 120 tons ish, right? And probably it's costing you, it's probably $20, $30, $40 for you to make it, and you are again selling it that plus 10% or something like that.
Yeah,
and that sounds like enough to satisfy the whole market you described, Aubert.
It does. So here's the other piece, Lucas. Right now, so especially let's look at the Korean ones, right? Because the Korean JV with SK Materials, basically they partnered, they've put in money, which means their customers have placed pre-purchase orders, or they wouldn't do that, right? Yeah. So for those three, for Samsung, LG, and SK, I'm blanking currently, but I know 2 of the 3 currently add 3 to 9% silicon in a lot of their current cells, like just their 18650s and 2170s at low percent. And what this would perhaps do at those percents, or maybe even a slightly higher percent, is just give them a little bit better stability with that same little bit of extra energy density, a little bit extra of charge rate that they want. I don't think we're going to go to, full silicon.
I mean,
that would be a perfect use for it. That would work out really well.
That's what I think is going to happen short term. Is it's literally just great. Throw in 10% of their stuff with 90% graphite, and then it's maybe it's a tenth of the EV batteries, and it's a tenth of the material in the anodes, and that's actually huge, right?
And I mean,
that sounds plausible to me.
This is my earlier comment about that's not their problem, right? Their whole thing is just making materials, right? I almost wouldn't even call them a battery maker. They are a materials maker, and they're servicing the battery market. And then whether that person puts 2% in or tries to put 100% in, they really don't care, right? Yeah. Because they're not making the anode, they're not making the BMS, they're not making the pack. They're just there to be like, we make tons of this, it works pretty well, use as much as you want. And a lot of companies want to get away from Shinetsu's silicon monoxide, right? Yeah. And if you look at all the IRA stuff and the funding that goes, you need a local US source that provides either a comparable material or something to replace the 3 to 9% that you're putting in, or you need something that's better. Because when it comes to SK Innovation or any of these tier 1s or Phrasis, which is a tier 2.9, right? Like they need to have a supplier because all of the markets right now are underserved, and they're all underserved regardless of the material, and everybody's just trying to make it be 1 to 2% better.
Yeah.
I consider Ferris as a tier one. They're Daimler's supplier for their EV program, you know.
Yeah. Well, so in like I guess I consider them maybe, you know, like a 1.9, like just because like when you look at the list of cell makers, they're what, 9 or 10 biggest. They're still there. They're a player. They're important. It's just not, you know, top 4 or 5, which really are the tier ones, right? But I agree with you. And also what's interesting is that they do a lot more faster innovation cycles, maybe I would say, at least in their US groups, where they do a lot of projects and a lot of silicon projects, right?
I think they've got one of the best R&D groups personally, but maybe that's just because I've got to know them and work with them, so I'm biased. Yeah.
I would actually argue CATL is probably one of the strongest R&D groups out of the tier ones. Mainly just because of the sheer amount of money they pump back into that program.
So that's true, but also I guess the thing is we have no visibility into that.
Oh yeah, 100%.
Not here, whereas Ferrisys at least has a group here, and I think probably a lot of people here in the ecosystem have worked with Ferrisys because they have, you know, a local branch. Probably a lot of people here know Maduri, who's been on these calls, right? So
they're willing to try stuff. Ferrisys is willing to try stuff, which is awesome.
I mean, it actually brings up a bigger question, right? When you look at like Group14 strategy, like I know we harp on them, like that they have to protect their IP and everything, but you know, at the end of the day, the market as a whole, if you look at it, is becoming pretty national, right? EV or batteries are becoming the enabler of everything, right? If we imagine a world without batteries right now, our laptops wouldn't be laptops, our cell phones wouldn't be cell phones, our smartwatches wouldn't be smartwatches, we wouldn't have electric cars. LEO satellites wouldn't be a thing. Like they are the enabler of pretty much all modern conveniences, if you think about it. A great example of that is if any of you guys have been in a power outage recently and tried to go like 48 hours without power to your home, and just think about all the things you can't do. Your Wi-Fi shuts down. You can't turn on like a hair dryer. You're suddenly losing like heating applications. Your fridge doesn't work, right? Like batteries are so critical right now that, you know, regardless of how we grade them and how much problems we see, like having local suppliers are going to be huge. And Aubert covered that with the American made. And that's only going to get bigger and bigger as we go on, especially with the supply line hits earlier. Some of you joined late, but you know, a lot of these, like copper is a big byproduct out of the steel making industry, right? So like if you look at it from that, most of the world's steel is from Ukraine and Russia, and I don't need to talk about that, but we already all know what's going on over there, right? So like suddenly the single cell components that make up, you know, the raws for your current collector, or they make up the iron for your cathode, they become expensive because the people in a global economy, right? The people making it. So Ferrisys is gonna make a lot of batteries for US things. I have no doubt. And there's going to be a lot of materials companies that are going to leverage on the American made idea to get there. StoreDot's probably going to become a pack maker, would be my guess. That handles BMS. All these things are going to occur just because of how the world economics are changing with supply chain issues.
When I just on this point, when I talked to Group14's, so it was 2 people, and one of them was their VP of strategic marketing. And one of my questions to him on kind of how they fit in the ecosystem and kind of what are they doing to compete on cost is he was very explicit. He's like, we are putting a local facility in Korea for Korean battery makers. We are putting a local facility in the US for, fun fact, all the same Korean battery makers. He wouldn't tell me that part, but they all have plants announced here, right?
Well, that's because of how JVs are set up in Korea, right? So if you guys don't know it, JV in Korea, they have to sell equally to everyone. It can't be they made a JV with SK Materials gets all their materials, and they have first claim on X production capacity. Everybody gets a slice. That's just how they've structured the policy in Korea.
Yeah, because again, they have multiple, you know, important battery companies, and they want to make sure that they all are successful, not just one of them, right? So. But that to me was just very interesting. And then, you know, fundamentally, another point they made, which I guess I kind of knew but hadn't thought about, is that right now, also a lot of the electric vehicle companies, so like Porsche is an example with this investment, they have to invest in their supply chain or they're not going to have material. So Tesla's very publicly doing this. They're investing in the lithium and the cobalt and the nickel and the mines and the processing and the lithium. And so for Porsche, what this kind of is it's securing the materials next year for the cells the year after that, for their cars the year after that. I mean, that's what this investment.
Look at the recent pivot by npower, right? npower is going more and more into being a cell producer because there are so many underserved markets, right? So like, if you think about it logically from that point of view, there is a huge dearth of demand that needs to be filled. And regardless of your product, right, they will take cells as long as they perform reasonably. Your cell phone doesn't need 1,000 cycles. It needs like 115. The United States government, it's been quoted for 200 and like 10, right? Like there's plenty of low cycle life, high energy applications out there that just need a battery that is tuned for it. It looks like we got a comment in chat. So
sorry,
what is the strategy for Group 14 to enter the market and supply chain? It's through their joint ventures. That is their strategy. Their strategy, if you guys were to tell me what's the difference between Sila and Group 14, I would tell you guys all that Group 14 is open source silicon. Their strategy to enter markets and stuff are purely through shaking hands and going in joint ventures with other big companies. Whereas if you look at like Sila is doing joint ventures with the end usage application. They haven't joined up with an SK Materials. They haven't joined up, to the best of our knowledge, of course, with any of those people that are kind of in the middle. So their way to get into the market is they're just literally shaking hands with big materials producers and saying, hey, we have something interesting, and proving that it is somewhat interesting and then having them help them scale it up. And that's their whole strategy right now. Whether that works 5 years from now, because they've shared an intimate space with these big players who can reverse engineer their technology, we'll see. I mean, that's why we put Group 14 in the manufacturing of the equipment, right? Because the process experts are probably at SK Materials and REC Silicon, right? They are the people who are going to be experts of taking that 120 tons a year and making 12,000 tons a year. Now, the question is the reactor that they produce this in and the materials that they produce it with bought off the shelf or made explicitly by Group 14, right? And that's going to be the big question that'll need to be answered in the future, because if they're buying a reactor off the shelf and all they're doing is chucking stuff into it, then it's not hard to copy, and somebody will make a build decision in the future rather than working with Group 14, right?
Thanks for answering that. This is Katin. So why is it that they did not, like, say, partner with other people in the middle or even the EV maker?
You don't want to over leverage yourself. They partnered with Porsche, which is an EV maker, right? So like that they did partner with, but the reality is you don't want to. And my guess is their partnership extends to Porsche's investing money to have first rights to a certain allocation of materials from Group 14. And the reason they didn't partner or like with other people, I guess they didn't need to, right? Like if I were at a battery startup and I had 400 million from SK Materials and Porsche, there's no reason to go elsewhere, right? And as far as why don't they eat more of the pie, right, beyond just materials and maybe the manufacturing equipment, that's because the more you eat, the more you over leverage yourself, right? It sounds really good to be 100% vertically integrated, right? Like kind of like what Tesla's doing, but it is extremely expensive. And when you are a startup, trying to reinvent every step of the value chain is almost impossible.
Yeah, so another piece of this too is that, really, I think a way to look at it is they were basically 4 years behind on timeline to Sila, who's doing everything themselves. And so in order for them to catch up and get into manufacturing, what they did is they went basically one step behind them in the supply chain to, okay, who makes the things we need? Oh, great, REC and SK Materials. They sold them on the performance of the material and either got help or proved the scalability and then got help scaling, and really were able to kind of add almost an additional margin on top of the things those companies were already making and wanted to scale and make more of anyway. And now they basically they're investing in a higher profit margin end product that sells products they already make, right? And lets them leverage their existing plants and existing partnerships. I think they just found somebody that was a really smart play to partner with. It's always good to work with people, plus or minus you on the supply chain or the end customer who can pull everything forward. And they kind of did both, right? They're working with the people who are kind of at the same place, but a little bit before them in the supply chain, and the end user that wants to pull it all forward. And then they found partners who are willing to, take chances and spend, admittedly government money, but take chances and spend money on using their material to prove it out itself. So I think they did a really good job.
Yeah, I mean, they are 100%, getting ahead through this strategy, right? Like, if you look at other companies that are making new materials, right, and we're going to categorize that as silicon, lithium metal, solid state, and anything above, there is really only one company that is ahead of them, and that is Sila. And that's because Sila has made it into an application, and Group14 is hot on their heels, right? Group14 is probably already in some applications, but in very small quantities, right? Or else SK and all of them wouldn't have the confidence to go build a multi-billion-dollar factory for that company, right? I mean,
and again, if that factory in Korea turns on in January and starts making materials, that means we're going to see cells late 2023, early 2024 with their materials in like mass-produced cells from those big companies.
Yeah, and it might be 3 or 4%, right? But the point is, right, they're getting in there. Now, this actually brings up like a greater question, which is what kind of technology is silicon, right? Is it a transformative technology or a value add technology? And I would lean more towards the side of it being a value add. And that's primarily because if you look at the battery space as a whole, the cathodes, it's a cathode problem, right? Like it's not an anode problem. It's not a lithium metal problem. You can enable those technologies against the current cathodes, but the current cathodes are expensive. They're only getting more expensive. They're only getting harder to source, right? So like, to me, companies like Sila and Group14 and Cuberg are really just value adds, right? They are additive value to the current system. They aren't transformative. And that's just because of what the cathode is in the state, in the places we know where the cathode is going in terms of, supply and access. Now, does that mean they're doing it wrong by going open source and catching up? No, they're going to start making money and generating revenue streams and making lots of money. And if their game plan is, hey, in 10 years, we've done really, really, really well, and we want to sell this off and be done with it, that's perfectly reasonable, right? There's nothing against that.
Yeah, thank you. Hey, I have a follow-up on the cathode, since you brought it up. So, all these people are making anode with high energy density, it's not a done deal yet. So right now, are they all using NMC 811 as the cathode? And how do they do capacity matching on that?
Capacity match. So if you talk from a full cell design perspective, capacity matching is pretty straightforward, right? You need X amount of materials per unit centimeter squared on a current collector to give you the same amount of material at a known rating of that material. So that's really straightforward. As far as NMC 811, it would not surprise me if this has been tested against NMC 622/LFP/LCO LMO high voltage applications. I'm sure they've tested it against the full gamut of cathodes. So they will probably use it in LFP, but even LFP runs into the NMC problem for a large extent of the issues. So, balancing the cell, all that cell design stuff is actually really straightforward, right? You're not talking about it in terms of, oh my goodness, there's a technical challenge. It's just knowing what the rating of the material is and then subtracting or adding how much you need of material per unit centimeter squared. But what it does transition into is something that Noman said about how do you deal with the expansion and particle disconnection. So the whole point of their structure, which is this whole activated carbon structure thing, is that you're encasing silicon inside of a carbon or an electronically conductive matrix, and you're adding in predetermined amounts of void And as you have a certain amount of void space, you accommodate by letting that void space for expansion. And as things break in each other, they're going to settle on something that's conductive. Now, cycle life is going to be a function, right, of how much you have in there and how well you can disperse it within the electrode. So like if 100% silicon, it's not going to cycle well. If it's 4% silicon, you can get really good cycle life out of it, out of the current cathodes. Let's see. Aubert, you're doing some of these. You want to talk about them?
Yeah, sure. Yeah, okay. So let me. I'm gonna message what I have and then talk it over. So basically, the questions I've been answering are, having looked at Group 14 this detailed, does it change our grading from anyone we've looked at before? And the answer is yes, because we looked at this one in more detail, right? So like previous talks, we would put like 20 hours or 15 hours of time per company each, maybe. And this one, I feel like I put like 60. So you just get a lot more, right? And so, we basically did a 35, 40-minute presentation on one company, and normally we do like 3 companies, 5 or 10 minutes each. And so just level of detail, level of preparation, level of research was much higher. And we've also kind of progressed our formats and our grading criteria. And so like we would never have graded Sila badly on using SilaNano previously, or how they protect themselves from foreign manufacturers, but we did to Group 14. So like the answer is yes. If we were to go back and regrade people now, which we've talked about doing, is just a ton of work. Even just that little tiny, just to flip back to this this screen right here. Just doing, where is it? This piece took me like an embarrassing long amount of time just to put together. Yeah. Just the updates on like kind of the core information, right? Where you have to actually find the real research. And the answer is yes, we would grade other people more harshly after having done this if we were to use the same criteria in the same amount of time. And then the other question was, I'm going to paraphrase what you said here, but basically the other question is, for startups with a promising material, how do they path against incumbents with gradual improvement? And what I started answering is that basically, if you have a 20, 30% increase in performance that you're developing right now, it looks really good right now compared to current technology, right? But the problem is the current technology the incumbents have, they're already actually here. They're producing here and they're already here. And every year it takes you to get to production with your improvements, they're already improving past you gradually. And so if you take 5 years to implement your 25% improvement and they're improving 3 to 5% a year, by the time you hit, they're going to be close or even the same level you are. And it maybe won't justify the higher costs or the startup costs or the premium you think you're going to get for your technology. So really quick adoption is key. And that's one of the things that I think is really interesting about Group 14 is all those other companies have been around for a decade, almost 2 at this point. And they've been around for, 7 years, and they go into real manufacturing next January, and probably someone's already going to be producing with their material in mass manufacturing. Yeah. And so that to me looks really good compared to some of the other ones.
Also, another one you got to deal with, right? That we don't talk about a lot, but I think it kind of leads into this manufacturing is scrap, right? Like we have no insights into what Enovix's scrap rate is, right? NMC cathodes traditionally have very high sensitivity to any kind of contamination. So metals off, slitting machines, et cetera, et cetera. And there's probably a certain particle size or something that they go around and they say, if, some QC guy has a spot test and he goes, if this particle is above this size, they shut down a line, right? So like a lot of industries are actually really sensitive to process and how you do it. So it's probably something we'll add in the future, but like process sensitivity of a known material system is a hugely important factor when it comes to looking at how you scale up and manufacture that thing, right? If the thing you make is inherently ultra sensitive to the environment and everything around it, it is hard to produce it at scale efficiently and at cost. But I think Brady here, how you evaluate the cost of silicon deposition. You can't spend $100 a kg for much of battery mass, and silane production and handling seems somewhat expensive. Seems to start to sell a lot of promise and futures. So the expense of the silane and everything else, the materials, let's solve the first thing, energy costs. If you look at Northvolt, the reason they are building where they are building is it has access to cheap energy. So that's step one, is you get cheap energy and you do it. If you go back, I think, Aubert, to the engineering into the box or the pain point slide, they are roughly 60 to 65% of the cost of the natural average for electricity, right? So like that's step one on reducing your material costs, is just producing it somewhere where energy is cheap. Step two is just bulk. Right. So like, who are they getting the powder from? Are they buying it from a Sigma? Is it a cheap powder, right? You can make activated carbon out of like basically sugar water if you really wanted to, glucose, citric acid, you name it. Also, there's a huge range of when polymers tend to carbonize, right? PANI, which is used for carbon fibers, usually you have to oxidize it at 300 C, and then you actually have to carbonize it above 900 to 1200 C, right? Citric acid you can do at 300 C, and you don't need a pre-oxidation step or like kind of a thermal annealing step. Silane gas is kind of the same way. It's all dependent on what form of energy you are using. So here we're using heat as the form of energy to crack it, but they might have something else. You can use microwave, you can use radiation, you can use electricity, induction, you name it. It all just comes down to your energy source. So there's a lot of ways to make it cheaper and cost competitive. And I think honestly, when it comes to Group 14, they're probably doing it through SK Materials and REC Silicon. And they're probably also getting discounts from those companies because they're the main input into that material. So they're probably taking a low margin hit on using it. What is the actual price of synthetic graphite with US production? Do you know this one, Aubert?
I'm sorry, what was the question? I've been answering stuff.
What's the actual price?
Oh gosh. Those can get really hard. And basically the issue is there's the publicly available price. There's the price that you buy in small quantities. Then there's the like actual prices the companies pay over multi-year long-term supply contracts, which vary with a million factors per the agreement. And it's really hard to get those final ones. And a lot of times they're also location specific. And so the price StoreDot gets in Israel versus the price that, I don't know, I'm blanking on where Ferris is producing. I know they have a lab somewhere in like Texas or something, but if they were producing there.
Guangzhou, China, and Germany.
I was just thinking of the US R&D facility, Luke. Remember that one?
Oh.
I thought it was Texas.
Hayward.
I know they have one here, but I thought they had another facility. Anyway, okay, so versus here in Hayward, right? Those are two very different shipping and imports and tariffs and distance equations depending on where you're making the material, right?
Yeah, also guys, I would say, you know, silicon isn't a higher energy system, right? It is a higher energy density system, right? It's not, you are fundamentally not getting more amps. If you take a cathode and you match it with silicon, you are fundamentally not getting more amps or watt hours out of that cell. All you're doing is taking down thickness and mass, right? So it's not really like putting in the same category of suddenly it enables higher energy is really wrong. Actually, Aubert had to walk me off a cliff last night because I was reading through so much marketing where they were like, this improves 30% energy improvements. And I was like, no, that's fundamentally wrong.
So this is just one of these issues where like everyone sees this, the marketing guy gets a hold of a technical report that they don't really understand and they change a few words to sound better, which they should not.
Mm-hmm.
And so like, you know, I don't think it was this specifically, but in one of these, there was something that's like, and enables 50% more energy. And Jeff was just like, I'm going to kill
them. What is it? Let's see. Brady also came on another one on the top battery cost. I noticed that Bloomberg NEF survey that the ex-China price average was greater than 2x the global average. Survey responses seem to be somewhat weighted towards subsidized Chinese batteries for use in China due to other people not reporting prices. Is that consistent with your experience?
It's hard to answer some of those without the numbers. In general, China has been highly subsidized for a long time in many places, typically in the refining processes and in the cell making, right? And so they acquire the materials from other places that they are able to sort of control the source from. They process most of it. Actually, you know what? Let me just, I literally have a picture of this on my computer. If I can pull this, my presentation won't stop. I think it's just right here. No, that's the wrong one. Anyway, I had this recent photo from LinkedIn on just percent of all the different types of components in China, and it was like 20 or 30% of the raw materials, and then it was like 80-something% of all the processing. And then the components, again, most of it, and the cells, it was like 80 or 90%. And so there's been an enormous amount of subsidization to get to that point, although some to most of those are gone. But right now, I think a lot of the issue is the electricity costs. So they've had some real electricity cost increases, blackouts, and problems that have affected them going forward. And so, like, for example, you know, high temperatures to do a lot of the graphites and carbons and stuff is now maybe more expensive, and they're not going to be able to be cost competitive on that anymore. Versus, like, if you compare that to maybe what France can do with 6 cents per kilowatt hour with nuclear power.
Natural graphite performance will never exceed 330. That's the theoretical. So the delta between 330 and 300 might get you a little bit, or 270 is going to get you a little bit more in these batteries. But guys, I mean, most of the improvements you are seeing today from batteries are coming from manufacturing improvements and cell design improvements. They've taken a little material out. They've increased the amount of material they can put in. They've reduced the weight of the tabs. They've
increased the size of the cell.
Essentially, it's tolerancing, right? They are increasing the size of the cell. They are changing the tolerances. Like, that's where you're seeing really all the improvements today. You're not really seeing it purely from the materials beyond the recent NMC 811. And we might go to 10 half, but like even that, they need to figure out how to make it. And that's going to be a super sensitive material and probably have tons of scrap when it first turns on and be prohibitively expensive in the processing side. The reality of the situation right now, guys, is as far as you asking us what the price of everything is going to be in the US, we're going to find out shortly. That's the reality. There is a lot going on. Things are getting more expensive. The US is turning on factories, and I'm sure you can all see the price of bacon going up every like week or so. And that is going to trickle and affect everything else, right?
One thing to just comment on is there's a lot of disagreement. So like we did at least we talked in one of our current episodes a couple months ago about a disagreement between, I want to say, Bloomberg and Benchmark Minerals on their different reports. I'm sorry, Goldman Sachs versus Benchmark Minerals on their analysis of production versus cost for a lot of the core materials for batteries, including, I believe it was the nickel, the cobalt, and the lithium. And you know, Goldman Sachs is like, everything's great, we're funding, prices are going to go back down, no worry, keep investing, everything fine. And Benchmark Minerals was like, no, this is a catastrophe, we need more money invested in this, there's not going to be enough supply.
Yeah, and you guys need a bit of context.
Those are both experts in their own respective field, looking at it from their perspective with their information and their money. And
you also have to understand,
different.
right? Like, a lot of these companies do not hire battery people to do the consulting. They are a room full of MBAs who source data, and they make projections based on a linear regression or some sort of curve that they do an analysis on raw numbers. There's very little context, right? It's like, what is it? Goldman Sachs in that report was like, oh, we're fine, we're going to be producing lithium right away, you know, and we have more than enough lithium. And the reality, guys, is it takes like 5 years to bring up a lithium mine. So if your problem is 3 years out and you haven't built the corresponding amount of lithium mines necessary to meet that problem already, or they haven't already been built, you're not going to meet that problem in 5 years or in 3 years, because it takes 5 years, right? What a lot of these companies ignore, and I think this is something Aubert and I harped about, is they ignore the time cost or the time aspect associated with how long it takes to build something, right? Like, a gigafactory isn't built in a year, right? Like, we have had, I'll give you guys a really relatable example. How long has the Cybertruck been told to be ready for next year production, yet we don't see them on the road? Think about it that way, right? Elon came out with the first demo and said, look, we can do this, and it's fantastic. And it's been what, Aubert, 4 years?
Yeah, about.
Right? Like, that's a great example of just the harsh reality of a lot of these projected reports, is they don't take into account scrap, yield, process sensitivity, how hard it is to source materials, how much money it's going to take to like do it. Like, if you go on Google and look at like the Tesla like yard for their new gigafactories, you can see they basically scrap frames. So how much money is Tesla spending per unit to just bring up a line to get to the right tolerances that they've set in their own design sheets to make those frames, right? So unless you bring time into it, it's a real problem. Oh, see, someone told me, what are present real challenges in graphite anodes? The challenge for graphite anodes is more related to how fast you can charge it for certain applications, more so than the capacity or anything like that. And that's almost purely a BMS issue, in my opinion.
Wouldn't SEI stability?
Graphite's actually really stable. Like, it's more stable at a constant rate than a lot of the other things out there, right? That's why I said it's
isn't it still what limits your fast charge rates
ultimately?
Yeah,
that's why I'm thinking, that's why I was pointing out that it's more of a fast charge issue. The problem you have is everybody wants, what's the average efficiency FCE? It's like 97.
Oh, sorry, I'm looking up that graph to try to share. Sorry, I wasn't paying attention.
What's the standard FCE of like an NMC graphite? It's like 97.
Oh no.
Off the top of your head. I mean, the point being, guys, is like your materials are going to have a fundamental trade-off from particle size to enable faster diffusion to tortuosity of the cathode to cost. And that's why, like, the biggest thing there is just optimizing those parameters. It's more so less on the raw material side.
What do you think of niobolts? Niobium. What do you think of niobolts, niobium titanium oxide to replace graphite? I mean, this is coming from Claire Gray's lab at Cambridge.
So titanium ain't cheap. Let's start with there. Titanium in any form is not cheap. It might be the most well-researched material, but it is not cheap. Niobium, also not cheap. And then two, do you know what the nominal voltage of that is off the top of your head?
No, but anyway, they just did a big Series A, and they are looking into small electronic applications. I mean, you have seen these companies like Shakti 3 and, promise a lot, but this one seems interesting material. They're trying to get into electric toothbrush, hair dryer, and small stuff before getting into bigger one.
I mean,
and
the material is interesting, but I'll just share immediately what I found.
Niobium has a very small crustal abundance in the earth. Even if you took all of it, it's not that much.
So what you can see here, guys, is just the voltage profile of titanium niobium oxide and carbon. You guys see this plateau right here at 1.5 volts against lithium? There does not exist an electrolyte or a cathode that pairs with that. So think of it this way, right? Let's think about it logically. If your graphite's nominal voltage is 0.1 volts or 0.15, right? And your nominal voltage of NMC is 3.8 volts against lithium, you're going to have a 3.6, 3.7 volt battery, right? If you pair that same thing with a 1.5 volt nominal voltage window against NMC, suddenly your voltage window or your nominal voltage of your cell is 2.83. So you lose 1.5 or 1.3 multiplier on your energy of the cell by going to TNO. So like suddenly your 200 watt hour per kg battery is 130. Becomes a lot less enticing at that point, right? Like what I would say, guys, is like a good general rule of thumb is anytime somebody that tells you about a new technology, understand what the working voltage is, and then understand what the nominal voltage of that material is and how it relates, right? If you have a 1.5 nominal voltage, you need to have an MNO cathode, which is at like 5.3 volts, even to get it into the same ballpark. But that cathode is low capacity, and any of the carbonated electrolytes you make nowadays will completely degrade at those voltage temperatures, and it's almost a non-starter. That's why the high voltage industry for startups and high voltage batteries exist. Aubert.
Yep, I finally found the article I wanted to share, and I'm sharing it. Mission achieved. But anyway, so this was just showing the raw material sourcing, the processing, which I mean, like those are very high numbers for some of those. And then again, the anode and cathode production, very high numbers in the cell production, right? So really what we're talking about everywhere else is displacing this by building out capacity. And the subsidies for these were like 15 years long-ish, right? And so, you know, people have started subsidizing them now heavily in India, places in Europe, now the US, but it's going to take time to displace that, especially with the material shortages. So I think it's going to have to start in the raw material sourcing, and then you can build out the local refining, which gives you a bit of a cost advantage, maybe. And then you can figure out things from there. But yeah, the nationalization of all of these things and the supply chain issues are very complicated and very interesting. And that's the stuff I like looking at. So anyway, just wanted to share this. And this is was posted here on LinkedIn about 5 days ago. People care, I could try to like link it in the chat, but.
So I guess to wrap it up here, guys, it's 1:30, and I know some of us want to get food. If you are on the West Coast, if not on the East Coast, maybe start making dinner. What the present challenges for graphite anodes are solely, the practical challenges are solely electrode design and determining the correct particle size distribution to cost ratio.
Particle size distribution to performance metrics sought to cost.
Yeah, that is the thing you're looking at, right? You can make the world's best graphite, gets 330. If you have big clunky particles, you will form dendrites at fast charge. If you have very small particles, you will get horrible FCE and kill the total energy of your cell and make you add more nickel to compensate, which then makes your cell more expensive. So the present real challenges are, how do I size the particles correctly and architecture the electrode correctly in order to enable it, right? And great example, NPower, Adrian's group. They are a great example of somebody who is challenging that ever real present challenge. And they do it, I think, through like a multi-slot die coding. No problem, Cassian. So I think any last questions before we kind of end it here?
I think, by the way, I think that's the link to the thing I just posted. Somebody check and make sure you can get to it, and that's not somehow linking through my LinkedIn, but a bunch of people asked me for it, so there you go.
I have a question about contracts. So for all the raw material contracts, I know they're like, I guess, controlled until a couple of years out. So why can't people just, when we really run out of materials, why can't people just break these contracts?
They
can, but so the issue is right now, the supply is limited, and you've already kind of sold what you have and will have that's built out for the next, whatever, 2, 3, 5 years. And so everything else you're building now, you're probably going to be selling at a higher rate, or trying to get the investment to build it out for somebody to guarantee supply. It just gets complicated, and there's also a lot of issues with price changes. And like one of the biggest complaints I've seen is whether, you know, almost no one does real fixed price contracts. They almost always do ones that vary with market. And so all of a sudden you might have a situation where you're buying a material that used to be $30 per kg, and oh God, nickel just spiked to, you know, 75. Well, okay, I've locked in the supply, but I can't afford to build cells with nickel for $75 per kg because I can't sell the cell for enough to make back the cost. So now all of a sudden you have a locked in supply agreement that they want out of.
I mean, has anyone here, just from the legal aspect, heard of force majeure?
Yes.
Yeah. So Linda, the only way you can really break a contract after you've signed it without going through the full extension of a contract is force majeure. Like a great example of force majeure is like, we are breaking the contract because a tornado hit our factory, right? Or like, we are breaking the contract because the places where we got our materials cease to exist, right? And that'll let you enact force majeure in the contract to break it. But to Aubert's example, if you're already supplied in that contract and locked in your supply, unless force majeure exists, you have no reasonable way. Now there might be like contingencies or like
You pay them 10% of the material. They
Exactly.
let
You have like break
there's-
conditions. It's pretty standard, but
there's lots
no.
of stuff like that. But then the issue is then that person needs to find somebody new to sell it to, and so a lot of this stuff, as the prices are increasing and the quantities are the quantities aren't narrowing in, but the demand is going up. Just a lot of these things are fluid and changing, and anytime things are marginal and changing and unknown, people panic and it gets complicated, scary, more expensive. People want more conditions to protect them, and then it takes longer to do contracting. So anyway, the answer is it's very complicated right now. And so I've done a lot of like real due diligence for companies. And one of the biggest things right now, if you're trying to get investment as a battery company, is have you locked in your supply agreements? Can you get materials at a reasonable cost for the next couple of years? And it's really hard to answer that as a yes, because unless you're a tier one, you don't have the clout to force them to give you a locked in supply agreement when their costs are going up as a maker.
And this is what's driving things like Form Energy, where they're like, we have rust batteries, right? We do iron and oxygen and water-based electrolytes, right?
And those are cheap and plentiful, and the costs are completely not change.
What you're going to see is almost a reversion to chemistries that were thrown away, but they are inherently cheap. And if space is not an issue, they will 100%, the market will drive towards those, right? Like grid storage, plenty of space. Why not? It's fine. We don't really care about volumetric. We just care about getting as much energy, right? The metrics change from watt hours per kg and watt hours per liter to watt hours per dollar per cycle.
Yeah.
On that topic, do you want to comment on sodium phosphate?
Oh,
that's all you, Jeff.
Oh God.
Okay. Well, while you do your research for that,
hold on. I got to do the one thing.
So sodium iron phosphate cathodes with a sodium hexafluorophosphate electrolyte and a graphite.
Hey, Luke, I think it'd be easier for you to tell us.
I was just saying it makes a battery like the rust battery you were mentioning, where you never run out of rust, right?
Yeah.
And like you can't even, like, every country has enough rust. Sodium iron phosphate battery is another one of those things where, like, even if you want to scale the whole grid for the whole world, you have abundant materials to do it. You know, it would be a lot of separator and a lot of carbonates and stuff, but none of the ingredients are rare or in low abundance. Yeah. They're all super high abundance materials.
So what I would say about sodium iron phosphate, and this is, guys, like me having worked with sodium a little bit, but also just a quick Google search, is really the biggest issues you're going to run into is just the capacity hit, right? And Luke, you're 100% right. Sodium batteries, like sodium sulfur, sodium iron phosphate, sodium magnesium, they may all become viable options in the future as people realize they do not have to buy a lithium ion battery for their application.
Right. Yeah, when you compare it to iron, sodium looks pretty good volumetrically in energy density wise. I'm not talking for EVs, but for things that are stationary. Like you mentioned, when space doesn't matter, sodium iron phosphate starts to look pretty good.
I mean, the issue, of course, is you're dealing with, like, I don't know what the counter electrode for sodium iron phosphate is, if they're just trying to run pure sodium, which has basically the same problems as lithium metal. Do you know what the counter electrode is?
They use graphite intercalation, and they form a SEI layer on it from decomposing carbonate esters to make the sodium decomposition products to coat the graphite. It's still weirdly exactly like a lithium ion battery, down to using sodium hexafluorophosphate electrolyte and carbonate esters. It's just a lower voltage stress lithium ion battery, except obviously there's atomic radius differences, diffusion rate differences, thermokinetic differences,
but curves are
I can comment on that a little bit, actually. There are a couple problems with sodium. One is that you get less sodium in the graphite by mass. You get less sodium in the graphite than you do lithium. So that's the performance is worse there. And the diffusion through the iron phosphate is worse. The preferred crystal structure of sodium iron phosphate is more different from iron phosphate than lithium iron phosphate is. So it wants to do a phase transformation after you intercalate, after you get it in there, and that causes a number of degradation issues as well as slowing down the.
Also, the curves are non-monotonic, which is always a problem. Having working in a non-monotonic chemistry, if your voltage profiles aren't a straight line for the majority of it, that makes BMS people's heads go splat. It also makes guessing state of health and state of charge and all that stuff a giant pain in the ass, right? Because
are you proposing swinging it more than one oxidation state or something? Because I was picturing using it as a single redox.
You think, I mean, in a single redox state is probably okay, but I was thinking about swinging it more just through like the quick look. But yeah, I mean, let's be real, guys. It has a place. That's what I would say. There is a place for a cheap sodium battery.
Well, one of the things that I've heard the most from people in grid and who are thinking about what to do for energy storage for grid, not residential, not local, not county, not municipal, not factories, grid, is basically, they said that basically the idea of EVs is the best thing that ever could have happened, because basically all the car companies and other people are going to pay to develop the new technologies. The cost is going to go down and then they get to buy the best choice. And that's really what we're seeing right now, is there's been so much money and excitement in batteries and funding. And now we're starting to see a couple of people who might actually have a winning solution, like Uniform Energy, who we talked about before, who after we talked about them, they just got what, $450 million to build out a plant. So like, that's really exciting. And it just shows that people look at, again, the, hey, energy density per dollar, cycle looks really good. And you don't need to be high energy density if you're just sticking a giant brick container out by a solar plant or
I mean, a lot of these orthogonal thinking points of what chemistry to use for what application are really going to change, right? Like Luke, you'll appreciate this one. Our Next Energy, right? They're pushing packs and like, it doesn't have to be one chemistry. Now, I understand that has different challenges associated with it, but like, it's definitely a better train of thought, right? You can bring price down, you can put in different cells, power versus energy, reduce stress on a certain set of cells, like all that stuff.
You can finally not destroy your entire pack and cell architecture trying to fast charge.
Yeah, exactly, right? Like you can be like, the person's accelerating, use bank one of super high power cells. Like you can almost treat the pack as grid, where you have frequency balancing and load balancing sets or like subs. And I think that's, to your point about sodium, to like everything, that's the way we're going now. Hey guys, we all thought lithium ion was the king. It has its place. It's not going anywhere. I like my cell phone being really thin. I do not want a brick phone. But like these chemistries, other chemistries have a place. Form Energy is a great example. They'll probably win the grid battle because they're ahead. Our Next Energy is probably going to go and change how packs are done for the better. Sodium.
Honestly, in how little time that they've been around, a lot of people I've talked to in the car industry are now looking at kind of doing similar things. I think just the concept of doing that has made such a big impact on how people think about and plan packs.
Like it is absolutely amazing to be in this industry and see how things are changing, right? It used to be, this is king. I would not be surprised if Tesla in 2 years' time bought a grid style battery system and started developing different chemistries, right? They upcycle, but those things catch fire, as we are now finding out. The one in Australia did, the one they built locally did. So I would not be surprised if they're looking at different chemistries now.
Does anybody know if sodium works? I mean, we all know sodium works in an NCM or NCA cathode, but does sodium work in a manganese spinel cathode? Because manganese is like $4 or $5 a ton, because it's a waste material that accumulates from iron refining.
Even lithium doesn't work properly in a spinel, let alone sodium.
Well, right, but that's because of manganese dissolution and the Wong effect.
So the answer is yes.
But sodium not break it. So it does work in manganese.
Yeah, there are sodium manganese oxide cathodes that exist.
So that would be
in
a way
research.
That would be a way to get significant voltage back over a phosphate cathode while still not ever running out of the material and being dirt cheap material.
If anyone wants ideas for a new company, just listen to Luke talk for about half an hour and he'll spit out like 5.
So I'm looking at a low cost sodium manganese oxide cathode. and I love researchers. This is one of the things you got to deal with research and always keep like a little grain of sand. But they're saying capacity of 219 milliamp hours per gram, but a watt and energy density of 602. I don't need to do the math for all of you to know that that is not a winning combo right there.
So real quick, I'm just going to change subjects briefly, just before we end up, closing out, whenever that is. We said we were doing it 15 minutes ago, and we're still here, but so we're going to be putting the video up on our YouTube channel. The link to that will be on the Battery Brunch Notes page and also our LinkedIn. And then we're going to actually put this presentation up as well for access there as well, so you can see the presentation we did. So just a couple things real quickly is I was just curious if people want to throw into chat or just say out loud. We did Group 14 because people asked for it. Oh God, you have 20 seconds. So basically we did Group 14 because people asked for it, and people have a different company or topic or technology that they'd really like to see talked about. Throw it in chat or just send us private messages. And thank you all so much for joining us for this. It was wonderful talking to you all.
Thank you all. All right,
Cheers,
cheers,
you guys are
everyone.
awesome. Love you guys. Thank you.
Thank you.
Great job.